This video is following our acid-base titration cheat sheet that we made in the previous video. And in this video, we're strictly just going to do some calculations, trying to apply what we went over in the cheat sheet and the different areas of interest during a titration. So let's take a look at some example problems. So this problem says calculate the pH at the halfway point and equivalence point for 100 milliliters of 0.1 molar HF hydrofluoric acid titrated by 0.10 molar sodium hydroxide. So it says calculate the pH at the halfway point and the equivalence point. So we see here that we have a weak acid. So we have a weak acid and a strong base. Strong base titration. So I have in another window, I have our cheat sheet that we went over, and this problem is referring to this situation here. So weak acid and strong base, and it asks us to do the halfway point. So here, which is right here, and the equivalence point or the stoichiometric point. So we're going to apply these bullet points that it says right here to this problem. So it says at the halfway point, the moles of strong base is half of the acid. So you're going to neutralize half of the acid. That's what this says. And you're going to turn half of your weak acid into the conjugate. And then your mole ratio, your acid to base conjugate ratio is going to be 1:1. And you're going to end up taking the log of 1, which is 0, so pH will equal pKa at the halfway point. So we covered all this in the last video. So we're going to apply that to this problem. And then in the next part of the problem, we're going to do this point right here. So as you see, there's multiple steps to do this, and it's a little bit tricky, which is why, it's why I wanted to make this video to go over how to do this. So back to the problem. And from the cheat sheet, it said that at the halfway point, so at the halfway point, our moles of strong base equals half the moles of the weak acid that we had. And it also said that was one bullet point that may play a role. This problem, that's not really going to play a role because it just asks us to calculate the pH. So the pH equals the pKa. So I just need to get the negative log of the Ka. So I'm going to take negative log of 6.8 times 10 to the negative fourth. See if I could type it in right. Okay, so I get 3.17. So I have 2 sig figs, so I should have 2 decimal places. So the pH equals the pK, which is 3.17 for this problem. Okay, so at the equivalence point, or stoichiometric point, let me go back to our cheat sheet here. So at the stoichiometric point, we have that the moles of strong base equal the moles of weak acid. But what we need to figure out is how much A minus we have. So if I go to this picture right here, this shows a particle representation of what's happening during the titrations. This is weak acid and a strong base. And you'll see at the beginning right here, it has these zoomed in windows right here. At the very beginning, it shows that we have all weak acid. And then here's the buffer zone where you have the weak acid. And see this hydrogen right here? It's taken off by the OH. So it's been neutralized into water. So this plus the strong base has become water. And so the other product you get is the conjugate. So you have the conjugate pair in this buffer zone. Okay, so at the stoichiometric point, this is how it zooms in right here. At the stoichiometric point, you'll see that you no longer have any of the weak acid that you originally had. So what you're going to have is just the conjugate. So we need to figure out how many moles of conjugate we created from the reaction. And then we need to get its concentration, and then we could run it through the ice table. So that's what it says to do right here. Okay, at the stoichiometric point, we're going to use an earth table and get the moles of conjugate, and we're going to need the total volume. Since we now have the conjugate, we need to convert Ka to Kb. Use the ice table. We're going to be getting our x value will be OH, so we'll have to subtract from 14 to get the answer. So let's go ahead and do that. So that's the conceptual part of it. So now we have to apply that. So at the equivalence point, your moles of strong base is going to be equal to your moles of strong base initially before the reaction. So I'll write IN for initial. Is going to be equal to the moles of weak acid initially, and this also equals your moles of conjugate base that gets created. So all three of these things are equal, and this is going to be what's on the final line of your earth table. So it's going to be like this, your reaction. So you're going to have your weak acid plus your strong base, and that's going to make your conjugate and water. Okay, so initially you have 100 times 0.1, so that's going to be 10.0 millimoles. And if it's at the equivalence point, then your millimoles of strong base are equal to your weak acid. So we're going to put 10 millimoles right here as well. So this is 10.0. Okay, neither one is limiting, so they both run out. Okay, so this will be minus 10, minus 10. Okay, and there's neither of that are left over, and this is going to be plus 10. So this goes to 10 right here. So what I wrote right here, the moles of strong base equal the moles of weak acid equal the moles of conjugate base, is this information right here. The 10 that you started with is equal to the 10 that gets added. These both go to 0, and then you create 10 of the conjugate. So what I wrote there is this information. So I wrote that these three things are equal. So that's what I wrote right here. Okay, and then that's true for that entire cheat sheet actually. So for all the different titrations that we have. All right, so we're going to create 10 of the conjugate, and this is important because as you saw in that particle view, this is the only thing there. This is the only species at the equivalence point besides water. So this is what's going to control the pH, is the conjugate base. So we're going to so once we have this millimole, we're going to get the total volume added. So the total volume is going to be our 100 milliliters that we started with, our 100 milliliters of HF. So that's going to be I lost track of my slide. So it's going to be 100 that we started with. Okay, so there's 100 in there. And then if the base is equally concentrated, then in order to get 10 millimole for the base, you're also going to need 100 milliliters of that. So it's going to be, your total volume is going to be 100 of the strong base of the NaOH. So, and we could see that from at the equivalence point, if you go like this, the moles of strong base equal the moles of weak acid. And if we substitute MbVb for base equals MaVa. So, and this is given from this, so the molarity is moles over volume. So if you solve for moles, then you get M times V. So I'm just substituting that in for this. So if we want the volume of base added that's required to get this to happen, then we take our molarity of acid, volume of acid, so 100 times 0.1, that's the molarity times volume, and divided by the molarity of the base, so we're going to move over MB right here. So molarity of the base is 0.10. Then we get 100. So I did it, more mechanically like that. Or you could just do it when you notice that the molarities are the same. And if it's 1-to-1, the reacting ratio, then you could see that you'll need the same amount of base. So our total volume is going to be 200.0 milliliters. And this is important because our concentration of the base, so we're going to take this number here. So we're going to take this right here and then put it in our ice table here. Okay, so we have our 10 millimoles divided by our 200 milliliters of total volume. Okay, and this is going to do what bases do. It's going to take some H's off of the water and make HF and OH minus. So we're going to try to get this number, the OH, on the E line here. So since we have a base, we're going to have to convert this to KB. And just to speed things up in the video, I'm going to do KW over KA. So that's how I'll get this number. So my KB, I did this ahead of time, 1.5 times 10 to the negative 11. Okay, so I'll go 1.5 times 10 to the negative 11th. (1.5 times 10 to the negative 11th) equals x squared over 10 over 200. So if I solve for x here, I'm going to use the assumption rule, so that should work. Then I get x is equal to the amount of OH, which is equal to 8.6 times 10 to the negative 7th. And if I take the negative log of that, I get my POH, which is 6.06. So now I'm going to subtract from 14 to get the pH. And the pH is 7.94. And you have to be careful when you do these, because sometimes you can go a little too fast and you can skip a step or just kind of lose track of what it is you're doing. So I did this, when I originally did this problem, I actually, I think I was just trying to go too fast or something, but I ended up, I got this answer and I was like, hey, wait a minute, why is the pH less than 7? I have a base, it can't be less than 7, it can't be acidic. And then I slowed down, I wrote out my ice table. Oh, that's right. My X from my ice table is my OH, right? Because the base is going to be making OH. So there's a lot of steps when you're asked to solve for the equivalence point. Just to recap, you have to get the moles of base created. So you use the earth table to find that. Then you need the total volume. So you're going to have to figure out, this one worked out real nice because the numbers are nice and even and round. So they're not always going to be nice like this. But you can tell easily from this one that you're going to need the same amount of base as you had acid to get this equivalence point to happen, to get the moles equal. So it's easy to tell your total volume is going to be 200. So you have your millimole over your 200. Okay, and you said you use your assumption rule should be fine, and you get your OH. And remember, you also had to get the KB here instead of the Ka. So a couple things to remember: get the millimoles of the conjugate, get the total volume, switch to KB, then you're getting OH. Okay, and then you can subtract from 14 at the end. All right, so I have one for you guys to try at the end. That's kind of like this, but now I'm gonna move to one that's a little more difficult. So it says how to calculate pH. Oh wait, so this one, it's really similar to the previous one. So I'm gonna skip on to one that's a little more little more difficult. So this one says, um, this time we have a solid. So we have 0.126 grams sample of an unknown acid was dissolved 25 milliliters of water and titrated with 0.0633 molar NaOH. The volume of base required to bring the solution to the equivalence point was 18.4 milliliters. So let's calculate the molar mass of the acid. So it says you're at the equivalence point, okay, when this much base is added. So I'm going to go back to, and we have a weak acid, monoproduct acid, and a strong base. So this is a weak acid, strong base titration. So I'm going to refer back to this picture one more time, our cheat sheet here. And this question is dealing with this box right here. Okay, and it's not asking us for the pH. It's just asking us for the molar mass of the weak acid. So if we use this information right here, you can get, just by the equivalence point, you could get, that's kind of why you do a titration. That's one of the big reasons, is you can figure out an unknown acid, you can figure out the molar mass. If you watch your burette and you get the volume and you stop it at the right spot, then you can get the volume of base it took to fully neutralize your acid. And using that information, you can get the moles of acid. So from the reaction, from the stoichiometry. Okay, so we're really just using this information to solve this question right here. So you'll see what I mean, hopefully. All right, so at the stoichiometric point or the equivalence point, we have our moles of base equals our moles of weak acid. Okay, and before I do that, I should probably write out what the final thing we're solving for. It says molar mass. So, as you have noticed in AP Chem, these problems, a lot of these problems that involve multiple steps, you can figure out kind of what you need to do by writing out your final equation for what you're trying to solve for. So, my molar mass is grams per mole. And a lot of times you have to ask, like, what am I given and what do I need to figure out? So if you reread this problem, you could see that you were actually given the mass of the sample. So you're actually given this value right here. So you're actually given the grams. So this is actually 0.1276 grams. So if we get the moles of what? Moles of acid. So we get the moles of the acid, you're done with the problem. And you can actually get it from the titration information. So you could get it from this right here. So moles of weak acid is what we're looking for. And it's given by the moles of strong base. And if we use substitution, so this is the same as molarity of base equals volume of base. If it's a 1-to-1 titration, so which it is, it says it's monoproduct. So molarity of base times volume of, or molarity of acid times volume of acid. So I'm going to write a reaction. So I tend to not really like to use equations. I try to use stoichiometry every time I can. So I'll write out my neutralization reaction. This is my unknown acid reacting with strong base, and it's going to make A minus plus water. And we're trying to figure out, using this, we're trying to figure out how many moles of acid there are. So my molarity of base is 0.0633 moles per liter times, and this is also useful in case it's a diproduct or triproduct acid. Then you could figure out the equivalence point of each individual proton. So it's much more useful to write out the reaction and do it the stoichiometric way. So this is times 18.4 times 10 to the negative third liters. So my liters will cancel. Okay, and this is moles of OH, by the way. And in my reaction, I have a 1-to-1 reacting ratio. So there's 1 mole of acid per 1 mole of base. Okay, I did this problem ahead of time, and I have 1.16 times 10 to the negative third moles of weak acid. So this number I'm going to put back up here to get the molar mass. So my molar mass is just 0.1276 divided by 1.16 times 10 to the negative third moles. And I get a molar mass of 110 grams per mole. I think I need a decimal there for my sig figs. Okay, so now we're on to part B, where the problem gets a little bit more difficult here. So it says after 10 milliliters of base has been added during the titration, the pH was determined to be 5.87. What is the Ka of the unknown acid? So in the previous part, it says 18.4 milliliters of strong base took us to the equivalence point where our moles of strong base equals our moles of weak acid. So here it's saying after 10 milliliters. So it's useful to figure out where we are on the titration curve. So if I'll kind of sketch a little one right here. So here's our weak acid. Here's our weak acid. And right here would be like 18. So that would be 18.4 milliliters. So if we're at 9.2, that would be 9.2 would be halfway. That would be the halfway point. Okay, and at the halfway point, the pH equals the pKa. But this problem is not going to be so easy because we're not after 10 milliliters. We're not. So if this problem said at 9.2, okay, the pH was determined to be like 5.2 or something. Okay, then the answer would be the pKa would be 5.2, and you just go 10 to the negative 5.2, and that gives you the Ka. Okay, that would be easy. This problem's not like that. So you're at 10 in this problem. So you're at 10 milliliters. So 10 would be like right here. So you're not at the halfway point. So this is going to be a lot more involved than just doing that. So we got to figure out what we're trying to solve for exactly, and see if we could come up with an equation. As you notice, we're actually in the buffer region upon 10 milliliters of the strong base. So we're in the buffer region. So we can use the Henderson-Hasselbalch equation. So we can use pH equals pKa plus the log of base over acid. So I'm going to rearrange this, and just like as you could see in AP Chem, you've probably noticed by now, these multi-step problems, there's usually a question within the question. So here's our question, and this is pretty easy to write an expression for. So I'm just going to rearrange the Henderson-Hasselbalch equation, and I'm going to move this term over here. I'm going to move this term over and go pH minus the log of base over acid. So I'm going to do that. And then I'm going to try to figure out what they gave us and what they didn't give us. So they gave us the pH. Okay, they gave us that is 5.87. And these numbers, we've done enough buffer problems to tell that these numbers are, if we can figure out these numbers, we're done with the problem. And these numbers are, the base is how much conjugate base after 10 milliliters of OH is added. So that is the question within the question. So it says what is the Ka, but really we're trying to answer this question, and we're trying to answer this question. So how much of the original weak acid is left after the 10 milliliters of base is added? Okay, So we've done enough buffer problems to tell that these numbers are determined. So these numbers here are from the reaction, which we're going to get from our earth table. It's from the F line. So we need to figure out the F line amounts of the two conjugates, and then we're done with the problem. So let's write out an earth table and figure out what we know and what we don't know. So it's this plus this, and we have the conjugate plus water. Initially, your HA, that's the number that's never going to change. What's changing is this, because this is being added from the burette, and this is the amount that, so you put some powder in here. It was, I think it was like 0.1276 grams, and then you dissolved it in 25 milliliters of water. That's in part A. And from part A, we actually figured out the number of moles present. It was 1.16 times 10 to the negative third. Here, what we how we get this number is from this information. So it says after 10 milliliters of 0.0633 molar OH is added. So I'm going to change that to moles. So I'm just going to go 10 times 10 to the negative third times this number. And so then I'll get 6.33. I'm going to erase this box that I drew. 6.33 times 10 to the negative fourth. And this number right here is going to be 0, because there was none there at the beginning. As you can see, this should go to 0. And then you're going to have some leftover acid, so that's going to be this number. So our final line is we're answering this question right here. And then our final line here is we're going to be answering this question here. And once we get those numbers, we can use this equation to get the pKa. So and then this will go up by 6.33 times 10 to the negative fourth. Okay, and this number, I did this ahead of time. I just subtract those two numbers in my calculator. Okay, and then I have the two numbers that, these are kind of like what I was saying, the question within the question. So this was actually easy to write an expression for. We just kind of rearranged the Henderson-Hasselbalch. And what that did was it kind of like shed some light on what we really need to try to figure out. So we listed the things we knew. All we knew was the pH. And then the things that we don't know, which are given from the reaction, the final amounts after 10 ml of OH was added. So I'm going to put this number here, and this number will go here. So let me go ahead and do that in the calculator. So I'll go 5.87 minus the log of the base goes over 6.33 times 10 to the negative fourth, divided by 5.32 times 10 to the negative fourth. Okay, and I get, my answer is 5.79. So after I use this equation, so I get pKa is 5.79, and the Ka is just 10 to the negative 5.79. So, and I have that done ahead of time. So I have it in my notes, if I could just find it. So the Ka is 1.6 times 10 to the negative sixth. Okay, so that's a tough problem. Level of difficulty is high on that one, and the I don't anticipate something being this hard on the AP exam. So fair warning. Ever since they changed it in 2014, you won't get something this involved. You This is probably more likely to be what you would get. You would get something like this on the AP exam. This one is a lot more involved, but it's a good question. It really challenges your knowledge of like where you're at on the titration curve. So at 9.2 you're halfway. This problem says 10. So you're in the buffer region. So you that gives you the idea that you can use the buffer equation. It's a Henderson-Hasselbalch, and then and you could rearrange it, and then it really tests your knowledge on figuring out like how much conjugates are there after 10 milliliters is added. All right, so I have one to try after this, and the two I have to try, the your turns, are just like the ones I did. So here's this one. This is like the first problem I did, and then this one is very similar to the one that I just did. So see if you can follow the notes, follow the cheat sheet, and see if you could come up with the right answer. So let me actually let me write the right answer here, so you guys can check your work. I don't usually do this, but so the halfway point here, you should get 6.04 the pH. And at the equivalence point, you're gonna make, this is a weak base being titrated by a strong acid. So you're actually gonna get the conjugate. That the only thing present will be this at the equivalence point. So you should expect your pH to be less than 7, and it is. So if you do this entire problem, I got a pH of 3.61. So see if you could come up with those answers. For number 2, your molar mass of the acid should be 202 grams per mole, and the Ka, it's real similar to the one I just did, is 1.8 times 10 to the negative 5th. All right, good luck on those questions.